In this screencast, we're going to be able to view the inside of the Earth and understand the outside of the Earth. And we'll learn this or do this by studying waves. The first thing we can look at are wave properties and wave characteristics. That we need to understand that a wave is simply energy traveling through a medium. A wave traveling through a single material travels at a constant velocity. So a wave traveling through, say, continental crust, presuming that the continental crust is the same material, is going to travel at a relatively constant velocity. But as soon as it travels through a different media, say oceanic crust, something's going to happen. The wave velocity is going to change. And we can say that here. When a wave travels into a different media, its velocity changes. When a wave comes into contact with the boundary, where the media changes, it must either reflect, refract, or actually can do both. And the further a wave travels from the epicenter, the smaller the amplitude, or the less energy it has. So here's some wave properties we can look at. We can call these up here at the top. We call these crests when we look at this kind of the sinusoidal curve. We call the letters at the bottom. I've got C and J here. These are troughs. We've got an amplitude. Notice it's from this dotted or dashed line. That's our amplitude up to A. We could say the dotted line to C. That would be its amplitude. And what's important to realize is that from A to E is what we'd consider or call one wavelength. We could say E to F would be one wavelength. We could say either from D to I would be one wavelength. And we'd say from C to J would be actually two wavelengths. Here's why. From C to here would be a wavelength, and from here to J would be a wavelength. Moving on. We can also look at the amplitudes. That the amplitude of a wave is related to the energy in which it's transporting. So low energy is going to have a low amplitude. And a high energy wave is going to have a high amplitude. So the closer we are to the epicenter, or the location of the rock movement, the greater the amount of energy, the higher the amplitude. Here's what we can look at when we look at a compressional wave or a longitudinal wave, in this case a primary wave. We get these what we call compressions and rarefactions. The compressions are the area where the coils bunch up, and the rarefactions are where the coils are pulled apart. And this happens very quickly. But if I look at this, I could say that the particle motion, my hand motion, is going to be in the same direction as the wave direction, traveling from left to right. And last but never least on this slide here, we can look at reflection and refraction, two very important wave properties. When a wave comes in contact with the boundary, this line right here is a boundary, it can reflect, it can bounce off. So here I have my red, right, these red lines, this wave hits and reflects off into this blue. So this is what we call reflection. It bounces off a medium or a boundary. And refraction tells me that it bends through a medium or a boundary. So notice the red comes into contact here. If it's transmitted or passes through the boundary, it refracts. So refracting, bending through a medium. So buckle up. You probably want to listen to this twice. Let's make sure we understand something. There's this value that I'm going to call an N value. So the material has an index of refraction. We're going to call this an N value. That the vacuum of space, we call it 1.0. It's got this value that is larger than 1.0, tells me that as a photon or light travels from space into our atmosphere, it refracts. It refracts into our atmosphere that we call air. And if it refracts, or if it goes into something that's got a higher density, or in this case a higher N value, like ice, it's going to have a higher, this value 1.31, it's going to refract even more. And therefore here would be water, and here would be glass. So these are N values, and these are just some common materials. So there's some rules that we follow. That when a wave travels from one medium that has an N value to another, its velocity changes. When traveling from a low N value, right, a low N value to a high N value, the refracted wave bends toward the normal line. So let's look at this picture, because right now I've just thrown a lot of information at you. I want to look here at the boundaries. Here I have air, and here I have glass. And I have light, right? Light is a wave, and we can study any wave by studying light as it refracts through a medium. So let's look at this one first. Light travels from air into glass. The normal line is a line that we would draw perpendicular to the boundary, right? The boundary between the air and the glass is right here. If I draw a line perpendicular, that's what's in red. This is what I call my normal line. So normal is perpendicular. The rule is that if it travels from a low N value of air, right, I get air is 1.0001, which is lower than that of glass. Glass is 1.5. So I have a low into a high. It's going to bend towards the normal line. Notice the refraction is towards this line here. And as it goes from glass back into air, it's going to refract back away from the normal line because it goes from a high end value to a low end value. So it's going to bend away from the normal line. So those are some basic physics concepts. So let's apply it here. So if I look at reflection, let's say light travels here. It hits this boundary. Some of it gets reflected. Some of it refracts. If it goes from air to glass, remember, air is 1.0001 and glass is 1.5. It's going to refract towards the normal line. From low to high, it bends towards the normal line. So let's apply that. Let's say we look into a body of water and we see this penny, or this could be a fish. That because the light here is reflected off of the object, it reflects as it goes from a high end value to a low end value of air. If it goes from water to air, remember the photon is bouncing off of this. We are going to view it as if it was here. So we're not actually able to see into water where objects actually are because of refraction, because of the end value, right? Their refractive index, in this case, as light reflects off it, it's going to, notice it goes from a high to low end value. It's going to bend away from the normal line. So notice it bends away from the normal line. Here's my normal line. We view the penny as if it's right here when it's really right here. Moving on. So let's apply how we use waves to determine what's taking place inside the Earth. We can look at reflection and refraction the same way we did with light as it travels through different materials. So P waves. So let's apply this to a concept of, here's the earthquake. The earthquake is always at the top of this picture for this cross section, this cutout. So P waves travel entirely through the body of the Earth, whereas S waves only travel through the mantle of the Earth. And we know this because S waves cannot travel through liquids. These are transverse waves. So the boundary stops the S wave entirely, and then it gets reflected back towards the Earth's surface. So let's make sense of this. I've got dark blue are my primary waves. Notice I see dark blue in the outer core and the inner core. But notice they're not stuck together. It's not like one consistent wave. And here's why. Because it's refracting. As it goes from one media to another, it refracts. It also reflects at that boundary too. I can see dark blue here as well. But the S wave is the light blue. S waves are going to reflect. S waves cannot refract because transverse waves do not travel through liquids. And as a result of this, I've got the sequence of pictures here. Here's where the primary wave is kind of infiltrating into the outer core and inner core. Here I have it traveling even further. And then notice I have it traveling even further yet. So it's going to find its way through to the other side of the Earth. And that's important that we call that example right there, we call that a shadow zone. And we can make sense of that as well. Moving on. What I want to look at next is this. Shadow zones themselves. That a shadow zone, according to this, right, we'll call this a shadow zone. It's simply the region or the zone in space within the Earth from where the epicenter occurs. So this is the earthquake. This is the epicenter. Because of refraction, P waves have these very distinctive shadow zones that no direct P wave makes its way here. Right? I see them here. You can see the P wave shadow zone here and a P wave shadow zone here. And that's the same concept. You get two primary wave shadow zones, where primary waves, they make their way through here, but the P waves have two zones that we call shadow zones, whereas the S waves have a much, much larger shadow zone. You see that? This is my S wave all the way from here, all the way to over here. Because S waves cannot travel through that liquid outer core. And as a result of that, you only get S waves in this region of the Earth. So due to refraction, one can get a detailed visual of the internal layers of the Earth, much like that of an ultrasound to see a baby. The shadow zone of the S waves and the P waves provide the boundaries for calculating the size of the outer core. The time of the arrival of P waves provide the density of the layers of the Earth. And the lack of S waves provides the evidence that the outer core is liquid. So waves tell us or provide us a tremendous amount of information. We can also study these waves on the Earth's surface. That the Earth's fractured surface, when we talk about plates, we'll really talk about plate boundaries. That we can talk about divergent boundaries, these are in blue. We can talk about convergent boundaries, which are in red. And we can talk about transform boundaries, which are in yellow. And you'll find that where we find plate boundaries, we find a very active, an active region of the Earth, particularly in terms of earthquakes. We also find volcanism here as well. But here I have where we find plate boundaries, we find earthquakes. And so where I see the dark, I find all kinds of earthquakes, and I find earthquakes along the plate boundaries for the most part. There's some scattered, intermixed in there, but for the most part we find earthquakes where we find plate boundaries. But we can also find shallow, intermediate, and deep. That earthquakes occur at different depths. Deep earthquakes are typically found at convergent boundary, where we find subduction, oceanic crust subducting beneath another crust. This region is common for intermediate depths as well. Shallow depths can also occur at these locations, but they can occur in many other areas in Earth as well. So here I can see the light green are the shallow earthquakes. Very common to have shallow earthquakes. The dark green are intermediate. We find intermediate at subduction zones. And then definitely where we find the deep earthquakes are where we find the, in black, where we find subduction taking place. So where you find your intermediate and deep, generally you're finding subduction zones. So the Earth's interior, that viewing the inside of the Earth is possible due to seismic waves. There's a tremendous amount of information we can determine from understanding seismic waves. We can actually put these very distinctive layers and depths to the Earth and determine its infrastructure simply by studying the waves. And last but not least, the wave behavior inside the Earth can be graphed and mapped very specifically. Notice S waves die out here at letter D. And that should be obvious to you because letter D is the Earth's outer core. It's liquid. Transverse waves cannot transmit into liquids, but primary or longitudinal waves can. So wave velocities change abruptly as they move from one layer into another layer. And this is where we find boundaries between different layers of the Earth that have different characteristics. Thus, we find a change in a media, and the velocity change reflects just that. So notice this really quick, maybe not a really abrupt one, but I see it more for the S wave velocity change, where I find letter B. And you'll find that letter B we can identify as a different layer. A would be the crust, B is generally the asthenosphere, and C is the mantle itself. And here, I can see that the mantle outer core boundary, we get a dramatic P wave velocity change. And that just distinguishes something dramatic that's taking place. And we also get that at the outer core, inner core boundary. And I can associate that with the velocities. So the velocity in kilometers per second, I can see that, notice the wave velocity is speeding up as it's traveling through the Earth until it reaches this liquid outer core and it drops down from about 14 kilometers per second all the way down to about 8 kilometers per second. A very dramatic sequence, a very dramatic velocity change, simply as a change from a media, from a solid mantle to a liquid outer core. You need to make sure you understand that we can actually map and understand what's going on with the velocities. You will be asked that on assessment questions. You will need to be able to interpret what is going on within this graph itself.